as with many people, I'm doing a few odds and ends at the start of 2024, just trying to sort things out. And I'm starting off with this little device here, which has been on my shelf forever and a day. I've just never got around to looking at, and my lab is full of bits and pieces that I've just never got around to looking at. So this is an active probe off eBay, and it's stated that it has a bandwidth of kind of 100 kilohertz all the way up to 1.3 gigahertz. Now, I don't really kind of believe that bandwidth, and you can actually buy the same probe with different claims about its frequency bandwidth. Some of them are just saying 500 megahertz, and that sounds more realistic. So I have already soldered a BNC connector on the end here. It's a BNC connector and an SMA connector on the end here, and I already connected up some power. Ready to use this because this doesn't need a power supply, it's an active probe. So what is an active probe? What do we use it for? Well, the answer is it's an oscilloscope probe, or you could use it on a spectrum analyzer or something like that. And its job is to make sure that probing the circuit doesn't affect the circuit under test. Because sometimes when you take your normal oscilloscope probe and just sort of stick it into your circuit, so a normal probe like this, and you just kind of stick that end on your circuit, actually you've got a huge length of cable, you've got capacitance, you've got all sorts of stuff that is going to change the behaviour of the circuit that you've just connected it to. You've always got to remember that when you connect a piece of test gear to a circuit, that actually that test gear becomes part of the circuit. So, you know, often we don't want that. So we can use an active probe. Now, when I picked this up on the shelf, I did manage to break it. It had a pogo pin soldered on the end, so I'm going to just replace that before I do anything else. The other thing that I've done is I've soldered on this ground connector just here. Now, I've seen two designs of these on eBay, and I will sketch out the circuit diagram for this in a moment or two and just explain what the difference is in the two designs. Okay, so I've just desoldered the old remnants of the old pogo pin off the back here. Now, one difference between this circuit and a lot that you see on eBay is it looks identical, apart from it's missing two capacitors on the input here, which are normally in parallel. So they put two like 1 picofarad capacitors in parallel. On the input, this one hasn't got a capacitor. Or has it? Well, yes, it has, because this pad is connected through to the circuit, and on the other side, this pad is not. It's literally just a pad on the other side of the PCB. So the PCB itself and those two pads are in fact our input capacitor. Now, that kind of makes me feel slightly nauseous because that's a huge pad. So the only reason I can think that they're doing that is because they've had bad frequency response with the low capacitors, and also because with little discrete capacitors, they couldn't control it very well with all the stray capacitance that's going on there. So I think that's why they've done it. I'm going to actually just measure that in a second or two, but I'm going to get the pogo pin on first, and then I'll measure that capacitance. And if it's more than 2 or 3 picofarads, then I shall be worried about its impact on the device under test. Anyway, let me get the pogo pin on. Stop talking, get soldering. So you do need grounding on this end, because otherwise you're going to have all sorts of signal integrity problems. Okay, let's have a look at the circuit diagram for this then. I'm just going to draw it out. I think I can do this. So looking at this from one end to another, what we've got essentially is we've got the power coming in, going through a diode, so it can't be connected in reverse. There should be a capacitor just here, but there isn't. It's been missed off the board, and it goes into a 7805 regulator. Now on one, the input, it's got a small capacitor here, on the output it's got a small capacitor, just as normal in the data sheet. And then we've got a slightly larger capacitor just here. Not sure how much more I can zoom in on this without it going blurry, but anyway, fingers crossed. Now I can't see at the bench what size capacitor that is, but let's say 10 microfarad or something like that. Okay, and so that's all the power supply circuit. And the power supply is going over to here. Now here we've got a bunch of 3 resistors. There's a little capacitor just here doing something, which I can't quite see at the moment. We've got another resistor and a couple of capacitors over here. So let's map most of this out at least and understand what's going on. We've got an input on our little probe just here, and it comes into the board and it goes through a capacitor. And as I said before, the capacitor is made up of the two sides of the board at the front end. If I look very carefully at this trace, I can see that it goes, one end goes into this resistor, and the other end goes right round and into one of the gates on this MOSFET. And I'm not going to show you me tracing everything out on this circuit board from this point forward, because it's kind of difficult to get everything on the screen all at once, really. So we're going to one gate of the MOSFET. Now the other thing is a 106. So I've got a few things going on here. I've got a resistor and then another resistor. This one's 6.8k, this one's 4.7k, and then coming off here I've got a 106, which is a 10 meg resistor coming down to there. So that's one end of that resistor that this entrance point comes to, and the other end goes up to this junction between these two resistors, and this end here goes up to 5 volts, and this end here goes to ground. Okay, cool. Now if we look at the MOSFET, we can see that actually this gate also goes up to 5 volts. Let's draw the rest of this MOSFET in here just so we've got it. And this goes up to 5 volts as well. So that's our drain, this is our source, this is gate 1 and this is gate 2 on our MOSFET. Okay, this comes down then, we've got 47. I would expect that to be bypassed, perhaps, which is indeed connected to one side of this capacitor and one side of this resistor just here. Yeah, and the other side of the resistor is there. So what we've got then, as I suspected really, is that we've just got a capacitor across here, like this, for the output coax. Okay, I think that's it. I'll draw a little circle around this. We can begin to just get a bit of a feel for what's going on, and these are going to be different values. So what's going on? Well, the idea of course is that a signal comes in here, this blocks the DC portion of it, and this is a very high impedance input into the gate here. Essentially it's infinity impedance in theory, but we've got a 10 meg coming over here, so in fact we've got 10 meg of impedance going on. So this is a nice high impedance input, which is exactly what we want if we don't want to be affecting our device under test. However, this capacitance here, yeah, it's very uncontrolled. There's two sides of this PCB, and it's not a controlled impedance PCB or anything like that. It's just FR4, and they're quite large. And although I've replaced the pogo pin going in to make it shorter, there was a bit of impedance kicking around there, inductance kicking around there. So I'm kind of feeling a bit questionable about that, because this capacitance itself will create loading. It creates both a phase shift and loading on the thing that it's going to connect to. So that might have more impact than I would like. So, I'm going to write impact on DUT. Okay, let's have a look at these resistors here. What are these all doing? Well, this is just a simple voltage divider. And if we've got 5 volts at the top, then I reckon that's about 2 volts just here, thereabouts. Not certain, but that's kind of just off the top of my head. In fact, let me do the maths. Oh, how close was I? Equals that times 4.7 equals, oh, 2.04. How close was that? Right, that's good then. So about 2 volts there. Now that means that also just here, that's also going to be sitting at about 2 volts in respect of ground. I kind of feel that it'd been better putting big resistors in here and then an inductor in here, in fact, would have been a better solution, in my view. But yeah, comments down below, as always. Okay, so let's have a look at this. This is a BF, I think it's a BF 998. And I have snuck a quick look at the data sheet on that, and yeah, I'm feeling unimpressed. So this is a 1 gigahertz bandwidth device. So the 1.3 gigahertz claim I'm very doubtful about, but the configuration of this, that bandwidth is going to matter less than I think, because this resistor is in the source, not the drain. So we're not looking at any gain here. This can't give you gain, this circuit. Yeah. So what is our impedance change? Well, we're switching down to 47 ohms here, which is near enough 50, makes no difference. So that's kind of what they're doing here. Now 47 ohms, however, I'm a bit worried about. And the reason is, this is a 30 milliamp device. So I'm going to actually run a couple of tests on this now in its DC setting. I'm going to get the multimeter out, and I'm going to probe a couple of voltages and just see where we are. So first of all, let's just probe this divider and see if we've got 2 volts there. So putting in volts would be a good thing. I know what I'm doing, honestly. Oh, how good is that? 2.05, and I said, well, I said 2, and my calculator said 2.04, so that is pretty much bang on. Now let's measure the voltage at the gate on here. Now there's a difficulty here, because this is a 10 meg resistor. So essentially you've got a 10 meg resistor going up to 2 volts. And what I'm actually going to do is I'm going to probe just here and here with my meter. But my meter has got a 10 meg input impedance in it. So that's equivalent to actually putting a 10 meg resistor in this circuit. So I'm actually expecting only to measure, although it's 2, I think that will be 2 volts because there's no current flowing through that 10 meg resistor. In fact, actually, I think I'm going to form a voltage divider with my meter, and it's only going to read as about 1.02 or something like that. So let's see if I can find it on the probe here. Not far off, 1.06, 1.07. So that's the impact of my meter on this device on the test, which, if you remember, I was saying about active probes, is exactly what they're designed to avoid doing. But anyway, there we go. So yeah, so we're also about 2 volts on here because we have to double whatever we read on there. Cool. So we're kind of beginning to understand how this device is now biased in its DC state. Okay, so what about this source then? Well, in its DC state, so this gate here, gate 2, is essentially turned on as full as it's going to be given the voltage that we've got here, 5 volts. So I'm expecting quite a few milliamps flowing because of that, and gate 1 is standing at 2 volts. So I'm expecting some conductance between the drain and the source, and let's find out what it is. If I can find that 47, and there we go, 0.93 volts. So let me just work out the current through that. So the current flowing through there is, give or take a few fractions, 20 milliamps. Now this has a 30 milliamp maximum drain, so that's absolute max. So this is really sitting a little bit closer to that than I would like. You can't take a very big signal in here before that starts to affect things. Now, one way that you could control that a little bit better is with this gate 2. So essentially, if gate 2 were, it's not really like that, but So if gate 2 were a voltage divider circuit, so we could change the voltage on it between 5 and 0 volts to, let's say, 4.2 or something like that, then we could potentially reduce that current flow here and change the DC point on here. Another reason we might like to do that is because we've just got 4 volts on here. Now 4 volts is in the linear region for this device, but you could do with a little bit more headway ideally. So if we had a little bit less current flowing through, then this voltage would be a little bit lower. On the other hand, there's a lot less room for that to wiggle around then. But as we're going to see, this doesn't have gain, it'll actually have loss in this circuit. So yeah, okay. So the only issue with putting a thing like that into gate 2 is that it will become interestingly frequency dependent, which could be a good thing or a bad thing depending whether we have to correct frequency problems or not. So what do I mean by that? So if I put a resistor in here, these two gates are capacitively coupled. They may be insulated from each other, but they are capacitively coupled. And so now we've got capacitance and resistance acting here. So now we're going to get a frequency fall off or a frequency gain, whichever way around it may be. I'm not going to try and work it out off the top of my head. But instead of this gate being connected to a low impedance, nice stable voltage, it's now connected to a high impedance voltage. And so it's going to play around in a frequency dependent manner. And so your gain is going to play around in a frequency dependent manner as well. So to be aware of that, really, you need a low impedance source there if you want to keep your frequency just dependent on this single gate. Okay, anything else that I'm worried about, really? So I'm a little bit worried about the operating point at round about 4 volts between there and there. It's a little bit close to the non-linear region for my liking. We might get away with it. So that could be improved slightly by changing the resistor here. But if we change the resistor here, we're likely to have to up the voltage over here. And actually, I think it's this voltage that's kind of creating the limitations in this circuit. So I'm expecting to see some THD because of the biasing of this transistor. I'm not really expecting to see much noise. This is a low noise device within its operating region in this circuit. There's not a lot of resistance around it that's going to create noise apart from this 10 meg over here, but it doesn't really take any current. So again, I'm not that concerned there really. How these capacitors all add up to a flat bandwidth, and this one just here, well, we wait and see. But, you know, there could be improvements. So to improve on this, how would you do it? Well, you'd probably really need, I mean, first of all, you want to reduce that capacitance a little bit if you can, but then really you would need a second stage. Well, this would be the second stage because it will do the impedance matching to the output. You would need a first stage ahead of it, which could do some amplification, not a huge amount, but amplification and frequency compensation to get everything good. But anyway, it is what it is, and for about £10, yeah, I'm not going to complain too much. Right, let's get on and see how it performs. So here we go, this is my first experiment, and this is going to be kind of its typical use for this probe, which is looking at a signal in a device under test and looking at it on the scope. So I've set this up. I have got a 10 megahertz signal flowing into this RF device just here. Now this is an RF splitter. It is good to 2.4 gigahertz, and you may have seen this on a previous program that I did. I'll link that in. But basically this is a Y splitter, so I have got 10 dB coming in, and on each of these outputs I've got 4 dBs going out, so it's splitting it between the two outputs very evenly indeed. So one of the outputs is going straight into the scope just here. That should be 50 ohm terminated, so I'll just do that. There we go. I'll just turn up that gain so we can just see what's going on. So there it is. The blue line is my signal coming from my signal generator through this splitter out and into scope channel B. On channel A, I've got a 50 ohm termination again, and we're coming through to our probe. And as we see at the moment, they're looking pretty flat. Both of these scales are set to 200 millivolts at the moment, and in a second I'm going to zoom in on the screen so that it kind of fills your view rather than just looking at all the experimental stuff, and then I'll show you the kind of results as I probe the circuit, and I'll tell you what I'm probing. Okay, so the plan is I'm going to connect up my ground, stick that in that hole there, that will do that job. It's on the ground plane, and then I'm going to connect the probe tip to the same output that's actually going across to the probe, to the scope I should say. Okay, switch across. Okay, and there we can see the signal. So the blue one is the signal coming directly out to the scope, and the center one, the yellow one, sorry, is from the active probe. Now both of these are set to ×1 at the moment, and they're both set to 200 millivolts per division, so we can see that the output from the probe is significantly lower. So I'm going to do some probe compensation, see if I can persuade it to, I'm going to do ×10 I think, and then we'll turn this to 200 millivolts as well. So now they're both at 200 millivolts, apart from I've got a ×10 compensation on my probe. So what am I like? Volt peak to peak 672 on the yellow, that's the active probe, and 928 on the blue. So I still need a bit more, so it's more like ×15, isn't it, I reckon. I don't have a ×15, and I don't have a custom on this one unfortunately, so ×20. Let me change this so that it reads 200 millivolts. So yeah, so it's about, I need about a ×15 ×16 adjustment to get this probe here to give me an appropriate, correct voltage reading on my scope. Let's change the frequency, however. So carrier frequency, I'm going to make that 100 megahertz, and I'm not really, this is the limit of this scope, so I'm in the 3 dB compression point of this scope already. But as you see, it's doing quite well. So I've still got my 20 times on my center line. Yeah, and that's doing about the same as it did before, slightly. Let's try and get my ground to stay connected. I really need about a ×18, something like that, to make them equal. Notice, however, that there is a phase shift going on there, and if I press the right button on my that this phase shift is actually changing as the frequency changes. That is pretty horrible. So there you go, you've got virtually no phase shift at all there. That is at 138 megahertz, which is really beyond the capability of this scope, but who cares? And then our phase shift is moving as our frequency drops. It seems like a good idea to use a pogo stick as a probe, but in practice, yeah, they're a bit weak. Anyway, hopefully it'll hold together enough for me to do the rest of the experiments. Okay, so for the second test, I want to look and see whether this impacts on the device under test. And so to do that, what I want to do is I'm going to take my device under test, which is the same Y splitter that we looked at before, and I'm going to pass a signal through it. And I'm going to look at that signal on this spectrum analyzer just here. So I'm going to sweep it from 10 megahertz all the way up to 1.3 gigahertz. So there it is. Hopefully you can see the frequency flatness just straight through this through connector. And what I'm going to do now is I'm just going to connect that, and you can see my signal source is set at -10 dB, and I'm just going to disconnect this, and our signal vanishes. I'll connect up this one instead. So this is the Y splitter, and on one leg, the same leg as before, we've got the 50 ohm termination, and we'll just run this onto this side. And we should be round about minus 6 dB straight across. Now it won't be flat, it's minus 6 dB, it's not quite horizontal. So I'm actually going to do something to this now, which is called normalization, which is where I'm going to have it do some maths on this line so that it brings it up to be a straight line straight across. And that way, when we plug this into it, what we'll actually be measuring is the difference that it makes to this. So it'll be a direct measurement of the difference that we're making. So let's do that. Let's first of all go to source, and then we normalize it. It says calibrate the through, so continue that. So essentially what it's done is it has removed that 6 dB offset that this is putting in, and has drawn a line right exactly horizontal on the 0 dB line. And now we'll have a little probe and see what happens. Make sure I'm turned on. Although it's not particularly visible on here, we can see that we are having some impact around here. About halfway, we're dragging the amplitude of our test circuit down. So remember that we have our signal just passing through this from our source to our destination, and we're probing that. So we're not seeing an output from this, we're seeing the effect that this has on that circuit. It's actually quite difficult to hold everything all in place all at once. But anyway, there we go. Right. So we can see it starts to tail off here at about 655 megahertz, and it's pretty bad. I mean, we're minus 3.4 dB up here at 900 megahertz. So minus 3.4 dB means we've more than half the power flowing through our device under test. So we don't want to see more than sort of half a dB or maybe a dB loss in our circuit. The impact is just too big after that. Let's say a dB for argument's sake. So let me make this scale better so that we can kind of see what's going on a little bit better. 20, there we go, 10 dBs. So, okay, so we're tracking pretty much flat across that 0 dB line. The first line down is minus 1 dB, minus 2 dB, minus 3 dB. Let's have a look and see how our circuit looks now. There it is. So that's what our signal looks like now. Oops, I've lost my connection. So let's bring the marker on, and we'll just go across to the kind of 1 dB mark, which is about there. We're about 1 dB down just there. And that's at 695 megahertz. See if I can get a good connection on there again. There we go. Now it does depend a little bit where I put my fingers in relation to this probe. So with some careful screening, we might be able to just eke another sort of 50 megahertz out of it or something like that. But that's our frequency response on the circuit under test. Remember, this isn't the signal going through our probe. This is the impact it's having on the circuit that it's actually probing. So we do not want anything more than that, really. So another bent probe tip. I'm going to solder a rigid probe tip onto this when I've finished, and the other thing I might do is put a resistor on the end. So why would I put a resistor on the end? You may well ask. Well, because it might actually reduce that a little bit, that effect that we're seeing on the screen there, because it will add a bit of coupling, so decoupling to that capacitor. It's actually that capacitance just there that's probably creating most of what we're seeing on the screen. So there's two things we can do. One is to reduce that capacitance, which we could actually do by just cutting this plate in half. And the other thing that we could do, which I might try, I'm just going to try that right now. I don't know if I've got a knife that's strong enough, but I'm going to give it a go. Interesting to see what it does. Just as an experiment, why not? You know, we can experiment as much as we like. there we go. And as you can see, we have actually extended that range out quite a bit just by reducing that capacitance at the front end there. So that's nice. Cool. Easy modification. If you've got the version with capacitors on, try fitting some smaller capacitors. See what happens. It might make it worse, it might make it better. But for the sake of 2 capacitors, do we really care? So now I've kind of extended the range of this through to, let's say for argument's sake, just here. This is nearly 800 megahertz now, so much better. Right, okay, cool. That's a success. And it only took a scalpel. I mean, literally, that was it. 1 scalpel. Okay, so not too bad on the scope. The spectrum analyzer, the impact on the device under test, which is a critical thing for one of these, is a bit iffy. So what I want to do now is I'm going to use this same circuit, and basically I'm going to disconnect this and put another terminator on here and connect this up instead. So let me do that now. So just unscrew this, and we'll take this one's terminator and we put him on here. Great. And then we put our probe on here. So now let's probe again. Okay, so what we're seeing with our probing this time is absolutely nothing on the screen, and of course that's because this loses a lot of dBs, so I need to kind of rescale this by quite a lot. Okay, so I've actually soldered the end of my probe tip to the device under test, which actually isn't that unusual. We're showing about 27 dB all the way along here. Now these are 3 dB steps along here, so we can see that we've got, okay, well 1.5 dB of flatness across my 800 megahertz range there, but it's certainly not flat at all. Now we can kind of see it a bit more close up, and over here it's definitely not very well behaved at all, is it? I mean, that's 6 dB difference at the 1.3 gigahertz end. At 66 megahertz, 26.8. So it's about a dB and a half difference. If you want to keep that within about a dB, then really you're looking at about using this as like a 500 megahertz probe. It all depends how flat you would like its response to be on your scope. You know, this is okay for your scope, I would say, as long as you don't want to make any accurate voltage measurements. But as we know, since our scaling is very difficult, we're not going to get that anyway. So there you go, outputting 120 megahertz notionally at 0 dBm, but in fact we're a little bit below that. And as we would expect, it does have a few harmonics present. Now this is currently just going through a normal through connector. So I'm going to take that through connector off in a second, and we'll put it through our instrument here. And what we're interested in is the size of these harmonics. So I'm actually going to measure them. I can measure them on here using harmonic distortion. And it's to its auto settings, and we'll change the number of harmonics to, I think, 3. Yeah, 3 will be good. And we'll adjust settings. And fingers crossed it should auto adjust and find those harmonics. So here's our fundamental frequency just here, 119.59 megahertz, thereabouts. And there's our harmonics over here. And it says its THD is 0.15% or minus 56 dBm. So I'm just going to write that down so that I can remember what it is, because I can't remember how to do the storage stuff on here. So it's 0.15% and 56 minus 56. Okay, so I'm going to connect my probe up, and here's our readings. So we're about 24 dB down as we expected. and first, second harmonics, and THD is now up to 0.36, which is minus 48 dB. Yep. So it's not actually dreadful. Minus 48 is sort of okay, and yeah, it's adding about 10 dB, or 0.2 nearly 0.2% to the figure, but it's not a disaster. It's not as bad as I feared it might be. Now it looks a bit noisier, of course, but yeah, that's okay. It's not a problem. But let me disconnect it completely and see if it makes any difference. And not really, I think, is the answer. I don't think I've got a terminator. Do with a little 50 ohm terminator on that. So if I just plug a 50 ohm terminator onto the end there, yeah. So the noise floor of this is actually below the noise floor of my spectrum analyzer. So let's sum up and bring this video to a close. So first up then, I suppose the first finding was the scope multiplier. We certainly got a perfectly clean signal on the scope, although it was quite attenuated, and we needed a scope probe adjustment of about times 16, which does tie it with the minus 24 that we read on the spectrum analyzer. Times 16, of course, is a bit of an awkward figure. And we've found as well that it's got a frequency dependent sort of phase shift. So depending on the frequency, the phase moves all over the place. So making a comparison between, let's say, an input signal and a signal in your device under test is going to be tricky. Impact on the device under test. This was the big test really. So does this probe actually load down your circuit under test? And the answer was it wasn't too bad. I mean, it always did, but it wasn't too bad up till about 500 or 600 megahertz. And then a bit of modification with a scalpel pushed that up to about 800 megahertz. In terms of the amplitude flatness, that was flat until about 600 megahertz. That's on the modified scope. It might be slightly worse on an unmodified scope probe. And the harmonic distortion wasn't too bad either. Certainly with an input around 0 dB. If you push it a bit harder, it might distort more, of course. But that's true of any probe. Noise wasn't a concern, and it proved indeed to be absolutely fine. One thing that it does need is perhaps a different probe tip. The pogo probes tips just kept breaking. I went through 3 of them in this video. You do need to attach a good ground to it, and you should keep that ground short. And it does need a screen case because there are proximity effects as your fingers get near to the various bits of the circuit, particularly towards the front end. So that's about it. I'll certainly be adding this probe to my toolbox, after a few tweaks that is. It's not a precision instrument, but certainly it's usable up to about 500 megahertz or so, and even beyond with some modifications. So I hope this was interesting and informative. Don't forget to like and subscribe, and of course leave comments. Take care, bye for now.